I have another fan today, but this one won't go anywhere very fast because it's too weak and too heavy, because it's the cooling fan of a disk drive. That's an 8-inch Fujitsu disk drive from about 1980 something. Do we have a date? Here we have a date, 1987. Here it is. 144 watt, and the power supply delivered 24, 5 and minus 12 volt. It's the model M2333K, and that means the whole disk here has a storage capacity of 337 megabyte. Not gigabytes, megabytes. So that means it's about half a CD. Oh, okay, about that. This unit was working until about last year. 1 month ago I tried to power it up, but the data was not readable anymore, and when I tried to format it, it turned out to have a lot of errors. So that means this is going to the final teardown. Let's talk about the interface before I take everything apart. The two connectors here, the big one and the smaller one, are a so-called SMD interface. SMD stands for Storage Module Device. It was invented by CDC, Control Data Corporation, and it works about like that. We have a B cable and an A cable. Oops, I have too much light here. Okay. The B cable is to transfer the data from the disk to the disk, and the A cable was used to control the disk, to tell the disk to which sector or block it had to go to. Was something about that. The A cable was routed from one disk to the next. So they did a daisy chain with the disk with the A cable, and that's the reason why we have here these terminators here, these 4 chips, or terminator resistor networks. And the reason why they are removable, they stick in the socket here, is because only the last drive in the chain needed them. So if this drive, for example, was the second drive and there was another drive connected after that, you had to remove these terminators, because you only terminate a data line at the end and not in the middle. While the B cable, that one, that goes here, is individual for each drive. So the maximum you can connect to one controller is 4 drives. That means you have one huge A cable here going from drive to drive, and then you have 4 B cables going to each drive individually. Then down here, the golden contacts is where the power supply connects. As I said before, we have 24 volt, 12 volt, 5 volt and a couple of grounds. Then there is another connector. This is only for the fan. There have been 2 types of fans. This one is a 115 volt fan, so the power supply does also supply the 115 volt fan voltage, AC of course. In other words, in a low voltage country like USA or wherever you only have 110 volts, you would connect the drive directly to the mains. And there was also a 12 volt fan version. For that you simply used another connector on the power supply. Well, I don't know what the benefit would be of a 12 volt fan, but you could have both versions. Okay, let's see under the cover. Cover slides off very easily. And you see an extreme amount of chips. Oops, that's too close. And they are almost all the old TTL gates, all kind of. So the entire interface board here is made more or less of TTL logic gates. I think from the configuration here that may be some RAM, probably. Looks a bit like that. What do we have? Some driver transistors for I don't know what, maybe some voltage regulation of some sort. Of course the 4 socket for the terminators. We have some dip switches here and also on this side. These are used for the geometry of the disc, the number of sectors and cylinders and stuff. Somewhere here the unit number must be set by switches. So if it's the first or fourth unit in the chain. Okay, let's see what's underneath that. We have 2 screws here and here. And then the whole, nice sound, the whole board lifts up. That's the back side of that board. You see some jumper wires, factory installed. As I saw on the sticker, this is a revision 2 or maybe 3, so these wires are possibly the difference between revision 1 and 2 and 3. That was the time you couldn't just reprogram some FPGAs or something like that. You actually had to take your soldering iron and change it on the hardware side. Now this is the control board. Some more voltage regulation. Some bigger chips here. I have no idea what they're doing. Power input, as I said before. Then that plug with the red and black cables goes down to the... There is another board down here, which is the motor driver board. We can have a look on that board by removing one screw here and another screw there. Maybe yes, maybe not. Okay, there is another screw. Yes, that's it. Okay, remove the fan. There's the power board. It has a couple of relays for the motors, especially for the spindle motors that drives the discs. We have a bunch of power transistors, also for the spindle motor and also for the actuator for the heads. Just in case you need a sound for your next horror movie project, this squeaking door, you can use this. Very nice, very nice. I like it. That's what I call mechanical engineering. Just look at this. I think that's the most rigid case you have ever seen, and this is not a car engine block. This is just a hard drive. That's what I like about these Japanese hard drives. They are made to perfection. Not only function, but also the mechanical, how they did it. So everything is polished, even inside you will see that. Even the parts that are not necessary to polish, but they just make it look good. And I think everything that looks good is also working good. Okay, when we have this side up, we will have a look what's underneath here before we turn it over. So what we have here is a solenoid with the mechanical kind of thing. That's the head parking lock. So that means in this non-energized state, the heads are locked in position outside of the disc or on at their parking position. And when the disc starts to spin, the magnet here gets energized. The heads are going free and they are free to move across the disc. This is a safety feature, just in case if you want to transport the drive so that the heads cannot slide across the surface without any spinning. That would scratch the surface and ruin your day and your drive. Here we have an air filter. This is necessary because when the drive warms up, the air inside the drive will expand and it must have a way to get out. Or, for example, if you move the drive from a low elevation area, perhaps into the Swiss mountains, there must be a way to for some air to get in or out, and that's through this very fine filter. Then we have here a carbon block. This is used to ground the spindle, because the spindle is turning on this ball bearing here. We can turn it now, you can see it, how it turns. So there is no proper ground because the balls inside here, they are greased. They don't make proper contact, so they installed this grounding spring here to make sure that there is no static electricity building up on the discs or something like that. This is something that is present on all the old drives. It seems the new drives don't need that anymore. Probably because everything is inside the drive. So that's the cable that goes to the motor driver board for this headlock solenoid. Okay, let's go to the interesting end. And open it goes. There is, of course, a rubber seal, which is now very sticky. There is another air filter here. This one filters the air that is circulating inside the disc. Okay, let's have a closer look about the air filtering system inside the enclosure. As I said before, there is an air channel going to the center of the disc, which is here. There is a gap here between. The air gets sucked into this gap, and to the centrifugal force here, it will be distributed between the discs. It will get back to this filter, going in here and then going back here, and there's the same kind of air channel on the bottom side here. And how is this working? I will show you that. I already removed a couple of screws. So that's the ring that holds the entire stack together. We have here 1, 2, and 3 points where the disc hub gets in contact with the disc, and here between is a gap where the air can flow down between the hub and the disc. By the way, this is the real rubber gasket here. That part on the cover was only the glue that was once used. There's another, oops, sorry, I broke it. Another gasket for the connectors. Everything. And just look at this, how thin this wall is. So that's the 8-inch diameter here. That's why it is called an 8-inch disc. And the whole disc itself is not much wider, only maybe 5 millimeters on each side. And there's the first disc. The second one is down there. Then we have a spacer, and that's what I meant. Even this surface here is polished, or at least turned on a lathe in perfect surface condition. For example, similar drives from CDC don't look like this. I mean, this side and this side, they must be flat, totally flat. But this side could be rough, but the Japanese are perfectionists. So let me get that air spoiler here out. That's just an air guide made of plastic to make sure that the air, I don't know which is what's the spinning direction, maybe that one or that one, so that the air gets between the head and the disc in a smooth way. Maybe this is to remove any turbulence, or I don't know exactly what it does. So the heads, you can see them here. In fact, that's not the head. The entire thing here, this rectangular thing, that's the head carrier. This is made in a shape so that air can get under it, between the disc and this air carrier. And when the disc is spinning fast enough, the airspeed will increase, of course, and this thing lifts off like a little hovercraft and creates a precise gap between the head, which is in fact here at the tip where the tiny little wires go in. Let me see if I can catch that with my camera. Okay, that's a nice view. You can see the rectangular head carrier with these 2 or 3 sliding surfaces that are mirror-like polished. And then the head is just at the end where the copper wires, the 2 wires, go to. That's the recording and reading head. There was a nice picture in those days to compare this performance of the head. They compared it with a Boeing 747, a jumbo jet, flying at 4 times the speed of sound in a distance of 1 meter above the ground, and the pilot is able to count every leaf of grass that passes by. That's about the performance of one of these disc heads compared in size. Well, that's pretty impressive. Now let's see how we can proceed. Before I forget it, there is another interesting detail on the fan. Well, the fan itself is not very interesting, but this thing here is it. That's an airflow sensor, and the way it works is, I think, so simple and quite a bit genius. There is a resistor which is connected to, I don't know, 12 or 24 volts, which heats up. There is a magnet with a relatively low Curie temperature, Curie point, and here is a reed switch. Now it works like that. This magnet is magnetic at room temperature, no problem, but when it heats up, because it is very close to this resistor here, the brown resistor here, if it heats up, because the air has stopped flowing, it will heat up, of course, because it's not cooled anymore by the airflow. When it heats up, it will lose its magnetic properties, its magnetism, because it's heated up above its Curie temperature. And when you heat up a magnet above its Curie temperature, it will be non-magnetic. If it is not magnetic anymore, this reed switch will disconnect, will open, and the logic here will sense the open switch and will know that there is not enough airflow through this sensor and will shut the drive down to prevent any damage, because behind this fan here is the motor driver board that produces a lot of heat, and also the whole logic board here produces a lot of heat. So that's a very simple and without any movable part except the reed switch contacts. They are hermetically sealed inside here. I think that's a very clever design and worth to have a look at. That's the head assembly. You can see there is the coil that moves the heads around. There are two super strong neodymium magnets. They are very nice to keep. They are really bad boys. Then we have the heads here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have the head read and write preamplifier, 3 SMD chips. They are moving with the heads for 30 years and more. That's the green wires that go directly to the heads, like here, that way. 2 wires, 2 heads. Then we have a flat ribbon cable, of course. And that's the wires for this solenoid, for this voice coil actuator. Bearings, ball bearings on each side. Very lightweight aluminium structure here. There is one special head. That's this one. It has its own surrounding here. I'm not sure it's plastic. I think it's some kind of ferrite. It has its own shielding against magnetic stuff. This head here is the servo head, and on the old drives you have one disk surface is dedicated to servo and tracking information, so there is no data written to that surface, and this servo head is only to find the correct track, to code the correct sector and everything. So if this head is damaged, you cannot read any data anymore, because the disk won't find the position on the disk. Well, that's it about the heads. Okay, and on this disk we can see the cause of the problem. I hope you can see that on your screen. Can you see these skid marks here? Yeah, I think now you can. That's the beginning of a head crash. It's not a very deep one, but it's already grinding the surface on a couple of positions, and that's a bad sign. We have more scratches here and here. That's what a good surface would look like. That's some scratches here. Yeah, that was definitively something wrong with that drive. That one looks okay. Next one, yeah, a little bit here, and a little bit more on this side. You can see it here, 2 scratches. Well, and there's of course no scratch on this side because there is no head on the bottom plate. Now that's the motor inside the hub. That's the headlock solenoid thing that we have seen on the other side. Well, I think that's about the interesting things here. There's one more interesting thing. The interesting thing is the ring, because with these rings you can make very nice mobiles. And they have 2 tones. If you hit them in this direction, you can hear that sound, and if you hit them on the radius, about here, you hear a different sound. You will be sleeping. You are tired. Oh no, I don't want to hypnotize anyone. Please wake up, wake up, wake up. It was just a joke. I have been playing with junk since a long time. Here you see the rings from a 8-inch drive, like the one I just disassembled. Then we have bigger rings from 12 or 14-inch drives. That's the ones I mentioned. They are not so shiny on the outside. That's a CDC product from the mid-70s. And they are all suspended by fine wires. And they make a perfect and nice sounding wind toy. Thanks for watching.